Everybody, in this video we're going to talk about solving equations. And before we jump into solving equations, I first want to talk about the use of variables in elementary school. So in this word problem, it says Allie has 4 cookies and her mom gave her some more. She now has 7 cookies and we're looking for how many cookies did she get from her mom. So, whenever you solve word problems or any type of situation, I would encourage you to have the students write out math sentences that represent the idea that's happening in the word problem. So, in this case, students are most likely going to think of this as an addition problem because you have 4 cookies, you're getting more, and then you have a certain amount that you end up with. And that's kind of the structure of how an addition problem works. And so the way that you could help your students write a math sentence for this is you could say, well, we start off with 4 and then we're adding some more, but we don't know how much more her mom gave her. That's what we're trying to figure out. So let's use a question mark since that's what we want to figure out. And the amount that she started with, which was 4, plus the amount that her mom gives her, which we don't know, that is equal to 7 cookies because she now has 7 cookies. So, what can we do to figure out what the question mark is? And you could go through and solve it that way. However, you could also use another way of representing the other unknown number. Because instead of using a question mark, you could also use a box where the goal is to fill in the box with the correct number, which in this case would be the number 3, because the only number that you can add to 4 to get it to equal 7 would be the number 3. So these are 2 ways you could write the math sentence with an unknown amount. And it is helpful if you feel like your students can manage it to start to introduce letters as variables as soon as you can. Because if you guys can introduce letters early on, it makes it much less overwhelming for the students when letters are introduced later in algebra. So, an example of how you could do that here is you could say, okay, Allie has 4 cookies to start with, and her mom gave her some more, but we don't know how much more. So, we're just going to use the letter M to represent that unknown number. And make sure you're really clear that the letter represents an unknown number. And so I like to use the letter M because it's what her mom gave her. And if you can relate the variable that you choose to what the word problem is talking about, for some reason that makes it a lot easier for students. So, like if her dad gave her some more, I might use the variable D. Technically, it doesn't matter what letter you use, but for whatever reason, it usually helps it make more sense to students if you choose a letter that corresponds to the word problem in some way. So anyway, you would say 4 plus this unknown number, which we're going to call M for right now, is going to equal 7. And then your goal is to figure out what M has to be in order to make the math sentence true. So that's just a little introduction to how you can use variables early on in elementary school because it will make it a lot easier for them once they get to algebra if they're used to this idea of using letters to represent unknown numbers. So the next thing I want to talk about is the idea of a solution. So a solution is a value that makes the math sentence true. So if we look at this first equation, you could technically say x equals 100. And in that case, you would be telling a lie because 100 minus 4 is not equal to 9. And so it wouldn't be a solution, even though you could make x be whatever you want it to be, it wouldn't be a solution for this math sentence because it doesn't make the math sentence true. And so instead, what we would do to find the solution is we want to find out what number x has to be in order to make the equation true. And in this case, the only number that could do that would be the number 13. In the second equation, though, there's actually 2 numbers that make this true. Because you could have, not x, you could have y equal 5 because 5 squared is 25. But you could also have it equal -5 because a -5 times a -5 is a positive 25. So that equation has 2 solutions. And this last math sentence has an infinite number of solutions because you could have z equal 9, or you could have it equal 8 or 7. It could also equal 10 because 10 is equal to 10. And this line underneath the less than sign means that it can be equal. You could also have numbers like 9.5, or 0 or negative 13. Any of those numbers would all make the math sentence true. And so they're all solutions. And pretty much any inequality will always have multiple solutions, or really an infinite number of solutions. So that's the basic idea of what a solution is. And with equations, we have the properties of equality, which says that if you add, subtract, multiply, or divide both sides of a true equation by the same number, then the resulting equation is true. So you can show this to students by using really, really simple equations. So you could use an equation like 24 equals 24. That is a true equation because 24 really does equal 24. And then you can show how all the properties of equality work. So you can say if I subtract 5 from 24, that gives me 19. And is it true that 19 equals 24? And you'd be like, no, it's not true. And you're like, okay, so I can't just subtract something from an equation and have it still be true. But what if I subtracted it from both sides of the equation? If I also subtracted 5 over here, then would I have a true equation? You'd be like, yeah, that's true, because 19 does equal 19. And then you could say, okay, well, what if I didn't subtract 5? What if I subtracted something different? What if I subtracted a 9? In that case, would that be true? And they'd be like, yeah, that's still going to be true because 15 equals 15. Well, what if I subtract 20? Will that be true? And after you've done enough of them, they'll be like, yeah, it doesn't matter what you subtract. You could subtract anything and it will still equal, or it will still make a true equation. And then you can say, okay, well, what about if I add the same thing to both sides? If I add 10 to both sides, will that make a true equation? They'll be like, yeah, that equals 34 and 34. Those two are equal. That's true. And you could say, okay, well, what if I add 5? Does that work? If I add 5 to both? Well, yeah, 29 does equal 29, so that's true. And then you can maybe like throw in a trick question and be like, okay, well, what if I add 1 to this side and I get 25 equals 24? Is that true? And they'll be like, no, no, that's not true because you have to add it to both sides. And you're like, oh, okay, so if I fix it and I add 1 to this side, does that make it true? And in that case, yes, it does. And so after you've done several with adding and subtracting, then you can continue the same process with multiplying and dividing. And what the goal is to see that if you have a true equation and you do the same thing to both sides of it, that the resulting equation is true. And it's interesting to note that the equations are not the same. Like, for example, if I took this equation and divided by 3, it gives me a totally different equation because the equation 24 equals 24 is a different equation than 8 equals 8, but the resulting equation is still true. And this is useful for when you're trying to solve equations in algebra. So, one of the ways that you can solve equations is by using the inverse operations to isolate the variables. So, in equations like this, the students can usually always do this in their head. And they can say, oh, well, I know that the solution to this first one is 5, and the solution to this one is 10. X would have to equal 10. And in this case, X would have to equal 9. And in this case, X would equal 30. And you can be like, yes, all of those are true. Those are all the solutions. And we need to figure out a way of figuring this out using the properties of equality because later equations are going to be way more complicated than this. And so you can teach them that this property of equality of doing the same thing to both sides of the equation can give them the solutions if they do the inverse operation of whatever operation is happening in the math sentence. So, for example, in this one, since you're adding 4, the way that you would undo the addition of 4 is by subtracting 4. And as long as you subtract the 4 from both sides of the equation, your resulting equation, which if you do x plus 4 minus 4, that's 0. Oh, sorry, x plus 0, which would be just x. And 9 minus 4 gives you 5. And so that resulting equation is true based on the equation that you were given, and that matches the solution that was found. And you can go through and do the same process for all of the other operations, like adding 8 to both sides gives you the solution of x equals 10. If you multiply both sides by 5, in this case, you get x equals 30. Or if you divide both sides by 2, in this case, you get x equals 9. So these inverse operations can help you simplify the equations to find other equations that are also true that make it so that you can get the variable by itself and find out what that variable is equal to. So once your students understand the idea of inverse operations, and this is usually an upper grade thing, so I think it starts in maybe 5th grade, but mostly in 6th grade. Um, but once they're good with doing inverse operations with just one operation, then you can move on to solving equations with multiple operations. And the way that I like to explain the process of knowing which operation you do first, if you have multiple operations, is that you work backwards of the order of operations. So remember, the order of operations is you work with the most difficult operations first, which are exponents, then multiplication and division, and then adding and subtracting. So when we undo the order of operations, we're going to work backwards of this order. So for example, if you have 4 times x minus 5 equals 31, the way that I would explain this to students is I would say, our goal is ultimately to know what x is. And if I did know what x is, the order of operations would have me multiply by 4 and then subtract 5, because order of operations says I should multiply first and then subtract 5. And whatever x is, if I multiplied by 4 and subtracted 5, my equation tells me that that would equal 31. And so if I want to solve the equation, I'm going to undo these calculations and work backwards to figure out what x is. And you can explain it as kind of like retracing your steps. So like if you knew what x was, you'd times by 4 and then subtract 5. So then we're going to retrace our steps by working backwards, and we're going to add 5 to both sides of the equation, because that will make it so that the 4 times x is by itself. Because if I simplify, and 4x minus 5 plus 5 is going to be 4x plus 0, which is just 4x. And then 31 plus 5 gives me 36. And again, remind students that you have to add it to both sides of the equation. Otherwise, the new equation will not be true. Then you continue working backwards, and you undo the multiplication of 4 by dividing both sides by 4. So you would divide both sides by 4, and 4x divided by 4 is just 1x. 36 divided by 4 is 9. And then you can check and make sure you did that correctly by plugging it in. And if you plug in a 9 for x, well, 4 times 9 is 36. 36 minus 5 really does equal 31. And so that would be the process of solving that one by using reverse order of operations. And you can do this even if you have parentheses, because a very common way of solving a problem with parentheses is to use the distributive property to simplify the expression and then solve it. But technically, you don't have to do it that way, because you could say, well, if I did know what x was, my first step would be to multiply by 5. Then I would add 1. Then I would multiply that result by 2, and then I would subtract 9. So that would be my process that I would do with order of operations because I'd simplify the multiplication and addition inside parentheses before doing the other multiplication and then the subtraction. So when you're solving this, you can work backwards and you can say, well, to undo the subtraction of 9, I'll just add 9 to both sides of the equation, which tells me that 2 times 5x plus 1 equals 32, I think. And then so I did that by adding 9. Then I undo the multiplication by 2 by dividing both sides by 2. So if I take 2 times the parentheses stuff divided by 2, well, 2 divided by 2 just cancels out, and I end up with 5x plus 1 equals 32 divided by 2, which is 16. Then I can undo my addition of 1 by subtracting 1 from both sides. And that gives me 5x equals 15. And then I can undo my multiplication by 5 by dividing by 5. And that gives me that x equals 3. So that's one way you can solve a problem like that. Another possible way, which is the more typical way, is to simplify the left-hand side before you start solving it. So in that case, you could use the distributive property. Sorry, I'm rewriting this here. So you could use the distributive property to simplify this expression, which would give you 10x plus 2 minus 9 equals 23. And then you could combine like terms to say positive 2 plus a negative 9 can be simplified to be 10x minus 7 equals 23. And it's important to note here that we haven't actually started solving the equation in the typical sense of using the properties of equality because we haven't done anything to both sides of the equation. We've just been simplifying the left-hand side of the equation. And once the left-hand side is fully simplified, then you would work backwards of order of operations and you'd say, if I knew what x was, I would multiply by 10 and then I would subtract 7. So to solve, I would add 7 to both sides, which gives me 10x equals 30, and then divide by 10 because that's going to undo the multiplication by 10. And that gives me the same answer of x equals 3, just in a different way. So again, most of you won't be teaching this because this is an upper grades topic, but it's still helpful for you to know it just in case you do ever teach sixth grade. And also, it's unlikely that you will be doing problems this complicated in sixth grade. They're going to be more like this. But it is helpful to know what they will be going into as they get further into middle school and high school so that you can give them a contextual understanding that will help those later concepts make sense. So I hope that this video is helpful. If you have any questions,